Hello and welcome back to the alphabet of astronomy. Today is brought to you by the letter V, and V is for Van Allen belts. Now this is such a cool topic and it makes me really sad that the only time it seems to come up is by people thinking that we didn't land on the moon. So if that's what you're here for, please know you're on the wrong channel. So what are the Van Allen belts and what do they have to do with the Apollo missions? The Van Allen belts are radiation belts around the Earth that contain a large amount of charged particles. Now we say belts, but they're really more like donuts. Primarily, there are two belts, the inner belt and the outer belt. Although, we actually did detect a transient third belt that lasted for a few weeks, and this seems to be something that can happen. The increased amounts of radiation in these belts represent a hazard to instruments and to people, and are definitely something we have to take into account when planning satellite missions, spaceflight, etc. Now, the Apollo missions were the first time that people actually traveled through the Van Allen belts. Now, the trajectory was chosen such they actually missed the inner belt completely, and they traveled through the outer belt fast enough that they didn't really receive a very high dose of radiation. In fact, the astronauts on the Apollo mission wore personal dosimeters, and so the entire dose that they received during the mission was measured, and it was actually pretty small overall, and most of that was not from the Van Allen belts. So the Van Allen belts were discovered back in 1958 by an American space scientist named James Van Allen. Wonder where they got the name. So Van Allen was a lead proponent for the concept of putting scientific instruments onto space satellites. Now this might sound like a pretty obvious idea to us now, but keep in mind this was in the 50s, back before the launch of Sputnik, so there really was kind of an open question on how to use space satellites. Now his instrument, a cosmic ray detector, was actually the primary instrument on board Explorer 1, which was the first space satellite ever launched by the United States just about 3 months after Sputnik was launched. Now this instrument on Explorer 1 actually measured a much lower radiation than was expected, and Van Allen proposed that this was due to saturation of the detector due to an increased amount of cosmic rays from radiation belts around the Earth. And then Explorer 3, which was the second successful US satellite, confirmed this hypothesis, and the Van Allen belts were first detected. Over 50 years later, in 2012, NASA launched the Van Allen probes, which were two probes on a mission to investigate the Van Allen belts. This mission lasted for 7 years until the probes ran out of fuel and made a lot of discoveries about the Van Allen belts during that time. For one thing, they discovered the presence of an unexpected third Van Allen belt that was transient and lasted for a few weeks following a solar storm. They also measured a lot of the different kinds of plasma waves that can accelerate particles that are trapped in the Van Allen belts. Now these plasma waves I think have some really cool names like hiss and Whistler chorus waves. I think that's cool. Anyway. They also found that the shape and size of the Van Allen belts varied a lot, not only in time, but depending on what energy level of particles you were looking at. Now this idea of charged particles being trapped in a magnetic field had been studied as far back as the early 20th century by scientists. The French mathematician Henri Poincaré actually solved the equations of motions for a charged particle around an isolated magnetic pole and showed that it would travel in spirals around the magnetic field lines. Of course, a magnetic monopole is a purely theoretical object and has never been discovered, and so a bit more applicable work was done by a mathematician named Carl Stromer, who actually investigated the motion of charged particles around a magnetic dipole. It turns out this is actually a problem that cannot be perfectly mathematically solved, but Stromer did find a family of possibly stable orbits that could exist. So the Earth has a magnetic field. It is a magnetic dipole, and these charged particles actually come from the solar wind, which is basically this constant stream of plasma that's being ejected from the surface of the sun. So these two things combine to form the Van Allen belts, where the particles actually travel in similar ways to what Stromer described. Now the detailed mechanisms of each belt in the Van Allen belt is actually slightly different. So the inner belt extends from about 1,000 to 12,000 kilometers above the surface of the Earth. However, that inner boundary can actually come quite low at times, as low as 400 kilometers, and this represents a hazard to things that are in orbit, like the International Space Station or the Hubble Space Telescope, which sometimes has to turn off its instruments when it's passing through these increased zones of radiation. Now the inner belt is actually composed primarily of protons. So these protons come from the decay of neutrons that are formed by the interaction of cosmic rays and the Earth's atmosphere. And then the protons get trapped in the magnetic field and form this inner belt. Now the outer belt extends from about 13,000 to about 60,000 kilometers above the surface of the Earth, although this tends to vary a lot because the outer belt interacts more directly with space weather from the solar wind. And it has a peak in the intensity of the radiation about 14,000 to 19,000 kilometers from the surface of the Earth. Now the outer belt is actually composed primarily of electrons, and these electrons are pretty much directly captured from the solar wind, and then they get accelerated by these plasma waves that accelerate them up to these very high speeds. But the Van Allen belts don't contain only electrons and protons, they can actually act as a confinement container for antimatter. So the Pamela experiment back in 2011 detected increased numbers of antiprotons in the inner belt of the Van Allen belts. Now, just like the regular protons that are in the inner belt, these antiprotons are produced by interactions of cosmic rays with the Earth's atmosphere, and then just like the regular protons, they actually get trapped in the inner belt on the magnetic field lines. Pretty cool. So radiation belts like this are found around every planet in the solar system that has a magnetic field. Sorry, Mars and Venus. But in fact, the term Van Allen belts only refers specifically to the ones around the Earth. So there you have it. The Van Allen belts are radiation donuts around the Earth that are formed by the interaction of the Earth's magnetic field and the solar wind. The increased radiation of these belts poses a hazard to both instruments and people, requiring additional engineering to protect them. However, they were traversed successfully by the Apollo program astronauts, and so they're not insurmountable. I hope you learned a little bit about the Van Allen belts today, and I hope you will join us again next time for the letter W. Thank you so much for watching. Have a good one. Bye!